Hey Chem 20s, Mr. Dukley here. This is very exciting because we are in a new unit. We are now all of a sudden in our stoichiometry unit, which is chapters 7 and 8. So this should be our blue booklet if you got it from the school. If you didn't get it from the school, that's okay. Remember, you can always get it off of our Google Classroom in the classwork section. Scroll down to the stoichiometry unit, and then there's a bunch of different ones. Just make sure you get the complete one with the title page, which will correspond to what we're doing here. So yeah, let's jump in and let's start off stoichiometry. So stoichiometry in general, that's not at all a felt pen. So stoichiometry, in general, let's get a nice color too. There we go. Is a method for predicting and analyzing the quantities of reactants and products in a chemical reaction. So it's all about analyzing the quantities inside of a chemical reaction. That being said, while we're focusing on the quantities and the big part of the unit is on the quantities, we need to know what those things are too, and we need to be able to identify them. So you see a little beaker or something like that, and you see a liquid and a little powder in the bottom. Do you know what's inside of the liquid? Do you know what that powder is? So while we are dealing with stoichiometry, it's mostly about the numbers, there's also a little bit about trying to figure out what the actual stuff inside of the chemical reaction is and what it looks like. And often we use diagnostic tests to figure that out. So some diagnostic tests that you probably have seen before is you can use a burning splint to identify hydrogen gas. So, and I think we may have done this one in our class as well. So if I had a test tube, here's a test tube. That's supposed to be a test tube. And I had a burning splint. So burning splint, some red for some flames, very nice. And if you were to stick that into there, into the test tube, you'd hear this pop sound. That pop is the hydrogen reacting with the oxygen, producing more water, and exploding fairly quickly. So you may have seen that, the glowing splint and the pop test. Or sorry, the burning splint and the pop test. Now if we had the same sort of setup, let's see, go back to here. Same sort of setup. So I have this test tube. I'm going to draw the test tube a little bit better this time, considerably better. And there's an unknown gas in it. One thing that I could do is I could go ahead and take, again, in this case, a glowing splint. So glowing. It's not burning this time, but it's glowing. If I were to put it into that test tube, that glowing splint would light back on fire if oxygen was in there. So lots and lots of oxygen. You probably saw in grade 8, you can use lime water to identify carbon dioxide. So you see a little jar and you've got some lime water inside of the jar. If you were to blow carbon dioxide into that, it would form a precipitate, and that's a test to see carbon dioxide, or sorry, a test to identify carbon dioxide. Cobalt 2 chloride paper is actually used to identify water, so it's almost like an indicator that we talked about last lesson. It's blue when there's no water, and it turns pink when there is water, and that's the way that they used to be able to tell, and they still might for that matter, used to be able to tell if you dropped your cell phone into like a puddle or something, and you're going and trying to claim warranty. It's typically, or at least it used to typically be, a little piece of cobalt 2 chloride paper to let them know, oh yeah, it's got water damage. Cool. So what we're dealing with here for this is similar ideas. The quantitative part, so the numbers, but we're also dealing with those qualitative, so those diagnostic tests to try and figure out what exactly is there. We're doing it inside of aqueous solutions. So our chemical reactions, they tell us a lot of information. So let's look at this one. I got solid copper reacting with 2 silver nitrates that are aqueous, so in solution. It's going to create 2 solid silvers and aqueous copper, looks like copper 2 nitrate in this case. That tells us a bunch of information, right? But not actually that much information. So what do these substances look like? How much of each substance should be used? Is it important that the silver nitrate has to be aqueous? Is it okay if it's a solid? What type of equipment do we need to do to make this work? All of these are great big question marks, and there's so many more. So a chemical reaction tells us a lot of really good things, but it's also missing out on some really, really important things. For example, it does not tell us anything about the temperature or the pressure. that it needs to happen at. And some chemical reactions need to happen at high temperatures or high pressures, or they just won't happen at all. It doesn't tell us about anything about the progress. So that's how long the reaction takes. Is it very, very fast? Is it very slow? Some of them are almost instant. Others might take years. So just think about a car rusting, right? A car rusting, well, it's a chemical reaction. It could take years and years and years for that chemical reaction to actually happen. It also doesn't tell us much about the process of the chemical reaction. So what is actually happening in the chemical reactions? What kind of things are switching? Are we expecting to see a lot of heat being given off? All of those pieces. How do we know when the reaction is beginning? How do we know when it's ending? So chemical reaction, our chemical equation doesn't tell us much about that. And then it also doesn't tell us anything about the measurable quantities of reactants in any form that you can use directly. So it doesn't tell us much information there. So what we're looking at is, well, how can we answer some of these questions, some of these unknowns? How can we look at those and help us out? To make this happen, we need to assume a few things happen in our chemistry courses. So we need to assume all reactions are spontaneous. What that means is they occur if things are mixed. So you put compound A together with compound B, and they react to make something different. You don't need to add a ton of extra energy or do anything extra special. We're also going to assume that they are fast. So it's not like your car rusting. You're sitting around there waiting for years for what looks like not much to happen. We're going to assume that they're fast. So as soon as you put those two reactants together, they're going to happen. And then finally, we're going to, well, not finally, but we are going to assume that they are quantitative, which means a reaction is going to keep going until one of the reactants is used up. So you react A with B, it's going to keep going until either A or B are gone, totally 100% gone. And then they are also stoichiometric. Uh-oh, I forgot. Okay, spelled it wrong already. Stoichiometric. There we go. Now, stoichiometric, what that actually means for us is they occur in simple whole number ratios that repeat themselves over and over and over and over again. And that's going back up to here. So if we look at our coefficients, it's 1 copper, let's get a different color, 1 copper reacts with 2 silver nitrates to make 2 silvers and 1 copper 2 nitrate, and it will always happen that way. Always, always, always happen according to the mole ratio. Cool. So as we get into this a little bit further, our chemical analysis, you know what, I'll probably just leave this section for you to read. It's just about different places that we could potentially use this and practicalities and combinations with technology. So I'll just leave that piece with you. But no, it is a big part of, well, your everyday life, even though you don't necessarily see it in your everyday life. There's a lot of things behind the scenes. So next thing that I want to go through and talk about is qualitative versus quantitative. So qualitative is all about the qualities, where quantitative is all about the quantities. So numbers, in other words. So today we focused pretty much 100% on qualitative analysis. And then the rest of the unit, quantitative. So today focusing on qualities, the rest of the unit focusing on quantities. So the first thing is, we can analyze a lot of stuff and we can identify things by colors. So solution color by itself is one way that we can identify very, very, very particular ions. And if we look at the picture up here, let's even just make that a little bit bigger if I can. Well, it's very, oh, there we go. It was blurry, now it's less blurry. So I've got iron 2 sulfate, sodium sulfate, copper sulfate, nickel sulfate, cobalt chloride, and iron 3 chloride. And we can have a look. Do you see differences between those? Obviously you do. Most ions are going to be clear colors, and we're talking metal ions here, by the way, as well. Most metal ions make clear, colorless solutions, but look at copper, nickel, cobalt, and iron 3. They definitely have some color, and there's nothing really else like that. So if we were to come across a solution, take a chemical, come across a solution, or sorry, create a solution with it, and it becomes a very particular color, there's a good chance that it's one of maybe a handful of different elements. You can find all of these ions actually on page 11 of our data booklet. Do I still have my data booklet open? So page 11 of our data booklet right here. So solution concentration. And notice it's not everything. So I got chromate ions, chromium 3, chromium 2, cobalt, copper, copper 1, copper 2, iron 3, manganese 2, nickel 2, and permanganate. So not many, but definitely a few. We can definitely tell what a few of those things are. Awesome. Cool. So it's pretty much what we're going to say there. The next one that we can talk about is the flame color. So this is now on page 6 of our data booklet. And again, this is for the presence of particular metallic ions. So essentially what we do is we dip a clean platinum or nichrome wire, so it's typically a little wire with a little loop on the end of it like this, and you collect some of your solution on the end. The solution is represented by red, even though most of the time it's clear and colorless. And then you essentially hold it in a flame, and you see what colors the flame burns. So you can see on here, like lithium, a nice red, sodium, a bright yellow. What would that one be? Potassium, I think that's purple. Again, you're talking to the colorblind guy here. Copper. Copper is everyone's favorite. That's why it says chemistry lovers. They love copper because it's this very pretty greenish blue color. Strontium, again, bright pinkish red, right? So again, it's not every element that we're looking at here, but a lot of elements have very, very particular flame colors. So I'm just finding page 6 of my data booklet, should be right in here, and we can see those particular colors. So lithium burns red, sodium yellow, potassium violet, rubidium violet, cesium violet, and so on and so on and so on, which is really, really neat. Okay, back to this one here. So the thing that I want you to look at here is these questions. If you do questions 1, 2, and 3 in the next minute or so, that's perfect. If you want to check out 4, it's not that much more difficult. Go ahead and check out 4 as well, but put the video on pause. And again, I'm expecting maybe 2-3 minutes to go through and find each of these. But answer question 1, 2, 3, and if you want to, check out question 4 as well. I'll have the answers afterwards. So go ahead, put it on pause right now. All right, so if we're back and we're ready to have a look at this, let's see, let me get a nice skinny felt pen. So expected color of solutions when we have the following: sodium ions, colorless. Let's see, we've got copper, typically forms blue, if I could spell. Iron 3 is sort of an orange yellow color. I'm going to get real lazy here and just write them out like that. We've got orange for our dichromate. Chlorine is colorless. Colorless. That one's kind of hard to abbreviate. Nickel is sort of a bluey green. Let's see. Okay, next one. What color is imparted to a flame by the following solution? So in other words, what color do they burn? So sort of a yellowy red. Copper typically forms blue. Copper 2 typically forms blue. Yellow for sodium. We got violet. Violet. There we go. For potassium, red for lithium, typically a very bright, pretty red, and violet for cesium. If you're back at the school, if we're back at the school next semester, you're going to see this. Just ask. It's pretty cool. I can show you this. So flame tests on solids actually produce the same color that they would on solution. So if the ion's burning, the ion is burning, is what question 3 is all about. So with this one, it gives us the full-on chemical formula that says these are some precipitates that have formed from some chemical reaction. Could we predict what color they would actually be? So carbonate, not on the list, doesn't burn in particular colors. Same with chlorine, same with sulfate, same with hydroxide. Notice it's always the metal ions, not usually, always the metal ions. So yellowy red for calcium. For lead 2, it should be a bluish white. For strontium, that's our nice red color. And for copper, that's copper 2. Typically we'd see like a greenish blue, green/blue, which is pretty rad. Okay, I'll just go over question 4 real quickly. It'll just take a split second. Fire logs. If you ever have artificial logs for your fireplaces, they're very, very common, kind of expensive. They often have chemicals in them to add some color to the flame. So a fire log has copper chloride at its core, sodium nitrate in the middle, and then strontium chloride near the surface. How would this fire log look? So initially, the outside stuff's going to burn, and initially the outside has strontium. So what color does strontium ion burn? Well, red. So initially the fire log would look red. So later on, it gets down to the sodium ions. Sodium ions being in the middle. And what color would they burn? Well, they burn yellow. So we turn from a red to a yellow. And then as it burns, finally it gets down to the copper. And this one's always, it's one of my favorites. I think it's because it's one of the ones I can see the easiest. The copper ions typically blue-green. I'll just skip the whole sentence I was thinking of and just say blue-green because that's what copper does. Cool. So there's a little bit. The last part that we really want to talk about here is the qualitative analysis by precipitation reactions. So a precipitate is a solid that forms in a double placement reaction. So you've got solution A plus solution B, and you mix those two things together. They obviously make a bigger solution. And typically you have a precipitate, this little solid that forms at the bottom, right? So we precipitate different things. What we do is we add very, very, very particular things to only try and precipitate out some of the ions that might be present. So as an example, and to make that very, very clear, in my test tube, I originally might have a random mixture of ions. I'm going to add some sodium hydroxide solution. Only some of those ions would react with hydroxide. Remember, sodium is soluble with everything, so it's about the hydroxide. And only some of those things would precipitate out. So over here we've got XOH, and X is just whatever element that is now precipitated out, but we still have some ions left over. So we can filter our hydroxide precipitates out. So now it's just ions in the solution, and I might want to add something else. So for example, sulfate ions I can add, and sulfate ions might precipitate the next thing. So now this might be YSO4. So now I got rid of all of element Y. I have remaining ions. I could pick something else that would then precipitate out those remaining ions. One of the problems and one of the tough things to look at, and realistically, I tell you, the only tough thing to look at for this is you want to make sure that when you add your negative ion, so for example, your SO4 to negative, it doesn't precipitate out everything. So if you're trying to figure out what exactly is in there, you have to be very, 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 and this is the next bit here, selective in the stuff you add when you're trying to precipitate. So let's go through and let's try and figure this out just a tiny little bit here. So what solution could you choose in each of these situations? This is example 1, to distinguish between each of the pairs of solution by using precipitation. So one of them we've got strontium ions, Sr2+, and the other one we've got magnesium ions. So what I want to do is I want to find something. Where's my periodic table here? And luckily we're on the right page. It's still page 6. And I think, what was it? Strontium, Sr2+, and I think it was magnesium, Mg2+. Go back there. I just want to double check that. Strontium and magnesium. What could I add to this that's going to precipitate one of those two things but not the other? Okay, so let's go through. First off, I might just skip this first section because pretty much everything's soluble with that first section. Fluorine, it says most things have high solubility except for magnesium and strontium. So if I were to add fluorine, because both magnesium and strontium have low solubility, fluorine's not going to work for me. They would both precipitate out at the same time. Cool, if I were to add chlorine, bromine, or iodine? Let's see. Most things have high solubility, and none of ours is there. So that one's not going to work. That one's not going to work. Okay, let's look at SO4. If I were to add SO4, most things are highly soluble, except for, hey, strontium's in there, but no magnesium. So if I were to add if I were to add SO4 to something that had both strontium and magnesium ions, the SO4 would precipitate out my strontium ions only, which is pretty cool, pretty cool. Okay, so now we can separate those two ions. So let's see, if we add SO4 2 negative, and typically what you do with this is we're focusing on that SO4 2 negative, the sulfate, but it needs to be in something else. So it could be like sodium sulfate or ammonium sulfate, right? Something from group 1 that doesn't really precipitate. So if I were to add some SO4 ions, we would precipitate the Sr2 plus, but not the Mg2 plus. So that's how we could separate those two ions. Pretty cool. Let's try out the next one. So I've got zinc ions, and I've got cobalt. Let's see, that must be cobalt 2 ions, because I believe cobalt has more than one charge. So zinc and cobalt. Let's go back to this. Let's just clean it up because it is a huge mess right now. There we go. So Zn2 plus and CO2 plus is what we're looking at here. So something that precipitates one and not the other. So again, I'm going to cross off group 1 stuff. It's kind of useless right now. Let's look at fluorine. So fluorine, no. Fluorine is useless. Okay, because everything, both zinc and cobalt, are going to fall under most. Let's see, same thing with this. Zinc and cobalt fall under most. Let's check out SO4. Nope. Useless. Everything falls under most. They're both highly soluble. You're not even going to get a precipitate. These ones, let's see, zinc and cobalt. Well, zinc is not in group 1. Neither is cobalt, and obviously not this. I think, again, a little bit useless. Okay, hopefully we're getting somewhere with this one. So it says, with iodate, cobalt is highly soluble, but everything else is not. Cool, so everything else, that must include zinc. So I think iodate, IO3 is the one that we're looking for. So again, I might add, and I'm going to add my balancing act for this, IO3, obviously aqueous, and that's going to precipitate, let's see, I think it was the cobalt, but not the zinc. Cool, precipitates the cobalt, but not the zinc. Should we do one more? We might as well, I guess. So I've got silver and sodium. Let's check out silver and sodium. This one might actually be super easy, because does anything dissolve well with sodium? Or does anything precipitate sodium? Not really. So I think this one, let's get rid of, nope, not an eraser. Let's get rid of all of this stuff. And we're just looking for something that will create a precipitate, not with sodium, but with, I believe it was silver, Ag+. So I'm looking along the bottom here. So this one, not so much. This one, I don't see sulfur there either. Or sorry, silver. Oh, hey, what's this? I see silver. I could add chlorine, bromine, or iodine, and any of those would precipitate my silver and not my sodium. Perfect. So let's add one that's fairly straightforward. So I would want to add NaCl, and that's going to precipitate. So the chlorine or chloride ion is going to precipitate the Ag plus out. So it's going to make solid silver chloride. Cool. Okay. So next piece that we want to look at here, hopefully this is making sense for people. Next piece that we want to look at, and actually probably the last piece that we want to look at for today, if I'm being totally honest, is we've got a solution that may contain sulfate ions and chloride ions. Cool, so may contain sulfide and chloride ions. Sulfate. We want to provide a flow diagram and a procedure that will determine if it has either ions, both ions, or neither ions. Okay, so this is a big one. So we are starting off, we want a flow chart. We're starting off with potentially SO4, 2 negative, and Cl negative. We want to add something. And when we add that, there's always going to be two options. So we have to think, we want to add something that's going to precipitate one of these things, but not the other. One, but not the other. So let's go back to our table here. Let's clean it up a whole bunch. And let's see if we can find something that's going to precipitate or that could precipitate one and not the other. So I think we had, what did we have there? We had Cl and we had SO4, 2 negative. I just want to double check that. I'll go back here. Yes, Cl and SO4, 2 negative. So let's check it out. This way is actually a little bit easier. I got Cl and I got SO4, 2 negative. So most ions are highly soluble. Most of them are highly soluble. Let's see. Copper is going to dissolve chlorine. And that's copper, by the way, copper 1. So I think copper 1 might be a decent choice because it's only going to dissolve my chlorine. Cool. And then let's see. Silver's on both lists, so that's kind of useful. Mercury 2's useless, sorry. Mercury 2's on both lists, so that's kind of useful. Lead 2's on both lists. TL, so I could use TL, calcium, strontium, barium. Oh, we got some options here. We definitely got some options. Cool. Let's start with something that's fairly straightforward, something that's easy to find in the lab, some calcium ions. Start with calcium, and then we could potentially have more than one right answer for this. So calcium ions. Where's the one? There we go. So we're going to add, and we'll put calcium. Let's do calcium nitrate, NO3. And the reason that I'm choosing nitrate is because I know that it doesn't react. It's not going to precipitate anything. Nitrate, literally nothing. So if we have a precipitate, so if we get a precipitate, what that means is the calcium is going to react with the sulfate, and we will have SO4, 2 negative, present. Right? If there's no precipitate, that means that there was no SO4 or sulfate ion present. That kind of makes sense, because the calcium's got nothing to do with the chlorine when I go back to it. Calcium is not one of the things that will precipitate chlorine. So if I add calcium and if we get a precipitate, it's going to be sulfate. If I don't get a precipitate, I don't have any sulfate. As simple as that. Okay, let's look at one now, because now we need to precipitate out and see if there's any chlorine, right, or chloride. So realistically, I could use any of these, any of those, but let's stick with copper 1, just because it's something that would not mess around with our sulfate. Let's keep it totally separate. So next thing that I want to do, now that we've figured this one out, the only thing that might be there is Cl negative. Again, we don't really know. So what we're going to do is we're going to add those copper 1 ions. So let's do CuNO3 again. So we're going to add CuNO3 aqueous. And again, if there are, excuse me, if there are chloride ions present, we will have a precipitate. So precipitate, if I could spell, tate, that means that Cl negative is present. And if there's no precipitate, no precipitate, that means that no Cl was present. No chloride ions was present. Cool. Now, like I kind of mentioned there was a bunch of different things that we could do as long as it precipitates one thing and not the other. So I randomly started with sulfate and I started with calcium because calcium precipitates sulfate but not chloride. I could have started with chloride and I could have used copper first, right? It doesn't really matter as long as it precipitates one and not the other. So I hope this makes sense for people. There's a little bit of practice for you folks to do. Let's see, I highlighted them here. I would say if you can figure out question 1 and question 2, and remember the answer keys are on Google Classroom. The page numbers, I should mention, don't match up perfectly, so you kind of got to sift through a little bit. The answer key corresponds to page 6, even though here we are only on page 5. So answer page 6. Page 5 to 6, actually. That's just because there's a little piece added into the answer key and not this one. But if you can do number 1 and 2 and you feel confident with number 2, that's awesome. Go for it. You're probably good to go. If you want a bit more practice, don't ask me why it starts at number 9 and number 10, but you can absolutely try out a couple more of those problems. But that is, and I think number 11 there as well, actually. There should be, yes, number 11. So anyways, that's it for today. I'm going to stop talking. I hope this makes sense. If it doesn't, please make sure that you ask some questions. Please make sure you get it figured out. And we'll talk to you again soon. Bye for now, Chem 20s.